how confident are we about our predictions? If I look outside, I can have a guess of what's the weather tomorrow. If I look at you, well, I can guess, well, it seems like a nice guy. If I look at my screen, I can hopefully guess that the screen will not turn down right now, right? And for all of these things, I have some sort of measure of how confident, how uncertain is my prediction, right? Now the question is, can a machine do that? Is it important that rather than giving me my best guess, a machine is also able to find the uncertainty around it? Well, I'm going to give you a few examples. Does it move? Do I need to do? Oh, yeah. OK, I'm going to give you a few examples. One example could be in algorithmic trading, for example. When you want to know the stock price in financial market, let's say in 30 seconds, right? You don't only want to know the best guess, you also want to know the uncertainty related with it, because you want to somehow be able to set up your hedging strategy, right? If you have your self-driving car, and this has to decide whether to do a maneuver or not, well, it needs to have some sort of measure of uncertainty, of safeness to decide it, right? And well, the third example that I'm going to do, I'm very keen on it because I'm personally working on it, and is when people are building, when engineers are building the first 3D printed bridge in Amsterdam, right? They do need a measure of the uncertainty for the defects, for the reliability of the material. Basically, you want to know the random defects at the micro scale that will have an impact on a macro scale. So for all of these things, AI is involved. And AI is involved, and it's getting more and more in our life, in our everyday life. And we can understand that it's more and more important that other than only one prediction, we will have a measure of the uncertainty around it. Okay? Now I'm going to change, hopefully, the screen. Yeah? And so you can see this nice plot here. Now, it could look like a target of some darts game, right? But if you're a bit more mathematical, you could see this as a two-dimensional, the contour of a two-dimensional Gaussian density. So how, without scaring anybody, how does it work? Well, basically, in the middle, in the center of these concentric circles, in the yellow area, you have your best guess, right? This is what I'm going to hope for, in some sense. And around it, you have your uncertainty. So basically, as I go far away from my best guess, the probability of the outcomes, the probability of the events, are going to be less and less likely, up to the border of my picture where basically my events are going to be almost impossible. Okay? So if my AI algorithm will find me only the best guess of this picture, that is the center, well, I'm quite happy, right? Already, I got my best guess. That's good, but although it will not tell me anything about the uncertainty about it, right? It will only give me a point, which is good, and it could be not good, as I said before. So one technique in general to avoid this problem is called sampling, okay? So what is sampling? Sampling is the ability to draw outcomes from a probability density like this according to how likely they are, okay? So basically, you do something like this, yeah? So you draw a bunch of particles. You draw a bunch of samples. And as you can see, these samples represent very well the Gaussian density that you see here, because the density of the samples is very high around the center of the pictures where there is a lot of Gaussian probability of mass, probability mass. And this density goes down and as you go externally to the external side. So these are samples, and in this way I can not only find the best guess of my picture, I can also have a measure of how uncertain it is, okay? Okay, but this is a very simple example. We know how to sample directly from a Gaussian distribution. It's not something very interesting. Although, if I move to the next slide and I go to this, well, this is already something much more difficult. We have no idea how to sample from this kind of density in a direct way. We need to recur to some more sophisticated method. It could be, for example, Markov chain Monte Carlo, if you heard about it. But what I'm going to talk about it now is another sampling method that it's called Stein Variational Newton method. This is our own extension to a family of sampling methods that has been developed very recently in the machine learning community, let's say the last 2 years. And I believe these are really cutting-edge research methods, so I'm very delighted to work on it. How does it work? Basically, you have a set of particles from an initial configuration, from a random configuration. It could be a Gaussian. And what you do is sequentially and deterministically, you transport them towards the target distribution. Okay? They start random, and deterministically you transport them, and they will represent that distribution that you see there. So instead of giving mathematical details, I will give you videos. Okay? So we go to the next slide. And I start with a random configuration of particles, as you can see here. And what I do when how do I start a video? Do you know how to start a video? Is there any answer? No, it's not for the, do you know technicians how to start a video? There, yeah. Yeah? Oh, there is a comment? Okay, it was very fast. But as you saw, these particles got transported, and the transportation was deterministic towards the density, the probability density, right? And the nice thing is that what you just saw, it was just 10 iterations of my algorithms. So if you're not familiar with sampling algorithms, I can tell you, in this case, 10 iterations is quite fast, okay? It's working very well, and the probability density doesn't have a very nice shape. It's quite weird in some sense, okay? So, well, I'm quite excited about it. So we are able to sample from a distribution. So in this case, we don't only represent the most likely event, which is in the yellow region, but also the uncertainty and the shape of the uncertainty around it. But in some sense, we can do more. We can do more. In a real situation, if you think about it, you are in some situation, you have some uncertainty about your events, and what happens is that sequentially, as time goes, you will get data, you will get observations, right? So I get an observation, and my best guess of something could slightly change in time, right? And the shape around my best guess, the shape of my uncertainty could change as well. And then I get another observation, and the shape could change again. Okay, and again and again. So what I will show you right now is that we are not only able to produce a sampling algorithm that converges to the right distribution, we are also able to produce a sampling algorithm that converges to the right distribution when this distribution is changing in time. Okay, this is technically called filtering. Okay, so if I go to the next slide. Let's say we start from a Gaussian distribution. As I get observations, this Gaussian will be reshaped in some strange way. Okay? Can you action the video again? Or yeah, please? Thanks. So as you just saw, basically, this Gaussian got sequentially, as observation came, got sequentially reshaped in some weird geometry. This is a multimodal banana shape, okay? And for a normal sampling algorithm, this could be already quite challenging in some sense because it's multimodal and has got some sort of strange curve shape and very thin, okay? I'm going to apply my algorithm again. So if I go to the next slide, and if it is possible to run the, yeah? As you can see, the particles can follow very well the change of probability distribution, the probability density, and in the end, they get to the right thing, right? This is quite cool. And what excites me, what for me was really outstanding, is that what you just saw was just one iteration of the algorithm at each stage of information, okay? So I have my stage of information. I perform one iteration of the algorithm. Then I have a new data. I perform one iteration of the algorithm, and so on. And with just one iteration per stage, I can get to that, which is, for me, quite good. Okay? Okay, now I will give you another example. I was quite jealous that around people can give robots and show like robots speaking and making weird facial expressions, right? So I decided to build my own bot. Something like this. Okay? Well, this is practically just a multimodal Gaussian, a mixture of Gaussians distribution. Here I basically created a few Gaussian and put them in order to do a phase. But it can do some weird expressions as well. So if you click on the video, you will see a disappointing expression. So it changes and gets disappointing. And basically, if I go to the next slide, this is a bit funny. I would like to activate it myself. If you click again on the video, please, yeah, you see that the particles follow very well the change of shape and can represent this, again, this distribution, but also the change in time. Then I'm just giving you really random examples. So I'll get to the next one. I have another expression. Can you click? Now it winkles at the audience to be cheeky. And so I go next, and please actionate again. And it follows. Well, I'll do the last one. Can you click? This is a bit of a mad, contradicting expression. And I will go forward. And can you click again? And again, the particles follow. So what I'm just showing is that it's quite reliable also for a mixture of Gaussians. Basically, when the support of the probability is, let's say, almost disconnected. We can say that, OK? So you have some different pieces of probability around. OK, so again, just to sum up what I just said, we have an algorithm that deterministically, from a bunch of particles, transports the particle towards the right density. I think I owe to the mathematician or the people a bit more mathematical, a bit of more detailed explanation of what I do, a very overview. I don't want to scare anybody, so if you don't like mathematical language, just close your eyes like this for one moment, and everything is going to be fine. OK? OK, so I'm presenting this Stein Variational Newton method, and this is a sampling method. And the main purpose of this method is the following. We want to find some transport map that I call T that potentially minimize some Kullback-Leibler divergence between the push forward of the current density of the particles and the target density. Okay? So to repeat, in some sense, I want the bunch of directions that move forward my current density of the particles so that they get closer and closer sequentially to the target density. Okay? And where closeness is meant in terms of KL divergence. Okay, this is the main purpose in some sense. And to find this T, we do it sequentially. So you decompose T in a sequence of simple transformation. And that's why you see iterations in my algorithm. Okay? So small steps. And those small steps will basically represent this small step size epsilon that I have at the end. Now, how? There is a tool used in this algorithm which is called reproducing kernel Hilbert space. This is a very well-used tool in machine learning algorithms. And it's built with a kernel. And this kernel has mostly two main roles. The main roles are it reweights the particles. In some sense, it reweights the contribution of the particles when they have to interact. And the other thing is that it creates a repulsion force. So the particles basically don't all collapse to the mole, to the best guess of my density, but they also spread around on the density to have some sort of measure of the uncertainty. Okay, this is the role of the reproducing kernel in the space. And the real improvement we did with this algorithm, our contribution in some sense, was deriving and including second-order information for this algorithm. Okay? So the basic algorithm was basically a steepest descent thing, was a first-order deterministic optimizing algorithm. And we derived secondary information so that we could use this secondary information in the optimization, so that instead of steepest descent, we do some sort of Newton-like update. And we also use the secondary information in the kernel so that we can reshape the kernel in a better way, and it's more efficient and more accurate in spreading the particle around the distribution. Okay? So given this, at the very end, we just basically update the particles. If my particle xi is going to be updated, it's like in any iterative optimization algorithm, it's going to be updated with a small step epsilon in the direction t, in the direction of my transport map evaluated at the particle itself. Okay, the very ending line. Okay, now pros and cons about this method. Well, pros, as you've seen, it's very fast. It's got a very fast convergence. So I'm very satisfied about it in some sense. And it's what we address as embarrassingly parallelizable. What does it mean? Basically, if your computer or your supercomputer has got many cores, you can basically send the work of each core, the work of each particle to a different core, so that the total computational cost is going to be overall divided by the number of cores, more or less, right? So you get a bit speed up, and it's important to develop algorithms with the arising of technology that have this property. And the third, if you want, pro is that it deals with some weird geometries that you just saw before. Contraries, well, this is a very new field, okay? It's cutting edge. It has been developed 2 years ago. And there is not much high-dimensional extension to it. We did some work in our paper, and we showed that the algorithm is actually scalable to high dimension, at least for some problems. But definitely a more comprehensive study of this thing, which is really where we want to go. We want to go to high dimension, is work in progress. And a second thing is also that, in some sense, it's a machine learning algorithm. There is not too much theory behind in comparison with other algorithms like MCMC, right? But again, it's a very new topic, and people are going to work on it. There is a lot of activity, and hopefully, we will derive some more theory for it. OK, I think I'm basically in time. I just put down my archive link to the paper, the list of my collaborations that come a bit everywhere in the world, the list of institutions involved, and thank you very much for the attention.